group generated by gamma squared acting on those. So we can summarize all these algebraic properties in a nice theorem. So where is it? Here it is. So theorem, a translation. Also, we can say, of course, obviously that if some other translation comes along, so let's say tau, a translation that's fixing the axis of our glide reflection. Translation fixing the axis C of gamma. Then we must have, then tau commutes with gamma. Again, make sure to show it explicitly, so work it out in details. But I will give some name to this translation, write it maybe as a product of two parallel lines. So work it out in detail and show that they do commute with gamma. I will formulate it in a theorem. I will put this result in the theorem. So a translation fixing line C commutes with a glide reflection with axis C. Also, we have that the square of a glide reflection, the square of a glide reflection is a non-identity translation. And finally, we have that a group generated by any glide reflection is an infinite cyclic group. A glide reflection gamma generates an infinite cyclic group gamma. Alright, so the steps of Winnie-the-Pooh group. Alright, so now we're ready to tackle, now that we have a good feel for light reflections, we're ready to tackle this major problem that is behind all of that, classifying all isometries. So we have to handle the free reflections in generically positioned lines, so lines which are neither concurrent nor parallel. So we claim, of course, that the result will be a glide reflection. How to show this? That's not hard. So if we have the product of three of three reflections, sigma P, Q, and R, let's assume first that P intersects Q. Clearly, they can't all be parallel or concurrent. Not all parallel or concurrent. So we first case, one of the lines, two of the lines must intersect, while the third cannot go through the same point. So assume first P intersects Q. So they cannot be all parallel, so assume P intersects Q in some point Q. So here's the picture. P, Q, in some point Q. So then we know for sure that the last line R cannot pass through the same point. So then we have this point Q is off line R, and we can drop the perpendicular on R. So let's call this M. And then we can rewrite the product of reflections on P and Q. How do we want to rewrite it? So I want to have M next to R. So I want to have M here. That's why I will write it as L followed by M, sigma L followed by sigma M. In other words, if we went in this direction from P to Q, then I have to have the same from P to Q, from L to M instead. So there exists, and in fact, unique line L, so that the product sigma P sigma Q is same as sigma L sigma M. Well, very well. Then we have that so this exists and unique. So then we have sigma R, sigma Q, sigma P equals to sigma R, sigma M, sigma L. And voila, we have a half turn around the intersection. So this is some M, and we have half turn around M following a reflection in L, and M is of L. Great, so we've written the original product, so the original product is equal to sigma M sigma L, meaning it is a glide reflection. Okay, but we are not done yet. Why not? Because what if P was parallel to Q? So we have to consider another case. So in case P and Q intersected in point Q, we have the glide reflection. But if not, well, if not, then they must be parallel. So if these two are parallel, then we have to have R intersect Q, because R cannot be parallel, cannot be a third parallel line. So third line cannot be parallel to the first two. So assuming P does not intersect Q, be parallel to Q, hence sigma, hence R does intersect Q. So if R intersects Q, then let's instead consider the inverse. So if we look at the inverse instead, so look at gamma inverse instead. So gamma inverse will be, of course, the inverses in the opposite